So, by now in organic chemistry, we have seen the structures of hundreds of molecules. And so, the question that should really be the burning question in your heart is what guarantee that do you have that those structures are accurate? So, this has bugged organic chemists ever since the beginning. When organic chemistry was a relatively immature field, chemists would determine the molecular structure by measuring a compound's physical properties. Now, we've done that a little bit, right? We've used melting points and things of that nature. And these early organic chemists would also carry out different reactions that were designed to provide information about the presence and the relative position of specific functional groups. So, for example, certain functional groups undergo oxidation and a color change with chromium. And so they would say, oh, well, this molecule has that functional group, and so we should see that color change. Now, as you might imagine, these processes were really painful for the chemists. They took a really long time, and they were very unreliable. It's one of the reasons why if you investigate vitamins, you will notice that we have some gaps in vitamins, right? So A, B, we have, vitamin A, vitamin B, vitamin C, but we don't really have a vitamin G, for example. And so when vitamin G was determined, they used these physical properties and they used reactivity, but later as better ways to determine chemical structure came along, we found out that vitamin G was really another molecule. It's one of the reasons why we have so many vitamin Bs, right? Is because they were discovered originally as other molecules, but then later as the way that we could determine chemical structure developed, we were able to go back and say, hey, these are all some derivative of vitamin B. So today, much of our knowledge about chemical structure comes from really specific instruments called spectrometers. Okay, and so we use these in analysis. So in typical analysis using a spectrometer, we are going to generate something called a spectrum. And the features of that spectrum are going to be correlated with certain characteristics of a molecular structure. And different spectrophotometers give us different information about the molecular structure. So in the field of organic chemistry, interpreting the features of such spectra is a very valuable skill. Now, this is also a very employable skill. No matter where you go from here, when you walk in to a job, they are going to train you on how to use an instrument. We were going to talk about 4 different types of instrumentation here. They're going to teach you how to do this. What they're not going to teach you to do is how to interpret the data or how the instrument works. And that's what we're going to do in these next couple chapters. Now, there are several places in the Nashville area that our former students have gone and are employed at, and a lot of what they do is spectrometry. Aegis is a really good example. A lot of students have gone and worked there. They do mass spectrometry, which we're going to talk about in this chapter. We've had students who've gone to work for the TBI or the State Department, and they also do quite a bit of spectrometry. And one of the things they report back is how they analyze spectrometry in this particular class really helped them in their current jobs. So this is incredibly important. Now, there are many different types of spectrometers, and the ones that we're going to focus on in organic chemistry are the ones that are most often used to characterize organic molecules. We're going to start with mass spectrometers, right? And the spectra they generate is generally called a mass spectra. We abbreviate this a lot of times as MS, and so you'll see that abbreviated as MS. The next type of spectrometry we're going to discuss is infrared spectrometers, which are called IR spectrometers, and ultraviolet visible spectrometers, which are called UV-vis spectrometers. Now, you should have had some experience with these in general chemistry. In chapter 17, we are going to look at nuclear magnetic resonance spectrometers. Those are abbreviated as NMR. Now, once you get and interpret these kind of spectra, it's very important in the context of synthesis. First off, these spectra help us identify newly discovered compounds in nature. So let's say you're out, you're exploring, you find a new frog, it's got some sort of sticky substance on its surface, and you want to see what that compound is, right? And so that's called a natural product. And so we have to identify what that structure is so then we can synthesize it from simpler compounds in the laboratory. A lot of cancer research is done like this. Now, what we find in organic chemistry, we're not going to go out and find these natural products at this stage in your career, okay? But what we do in organic chemistry, for example, is we, at this stage, are reacting A plus B, and we want to form C. C is what we're looking for. But what we also find is that we get like other things, D, E, and F, and nobody wants D, E, or F. Those are called side products or not really what we're trying to synthesize. So the very first step that you go through is you want to go through something called a separations method. You want to separate C from everything else. Now, we have done some separations methods. For example, we have looked at distillation, right? That's something that we can separate. There are other methods that we'll see in here. Gas chromatography is one that we say that's GC. If you've been in other classes, you've probably talked about high performance liquid chromatography. It's a way to separate out liquids based on their solubility. So there's lots of different ways that we can separate C, what we're looking for, from D, E, or F. You can take whole classes on this in graduate school. It's called separations methods. That's it. Now, once you separate out C, you have to prove it, right? You have to prove, and that should be an exclamation mark. We'll make it a very exciting exclamation mark there. You have to prove that that's what you have synthesized. And so the way that you do this is using spectrometry. Now, what we're going to find is there is not one end-all, be-all spectrometry method that we can use to determine the chemical structure. And so instead what we do is we use 2 or 3 combinations that each give us pieces and point to the identity of that structure. And so that's why we're going to learn these different types of spectrometry. So, as we mentioned before, these types of spectrometry have everyday applications. They're in criminal investigations. If you get an unknown substance at a crime scene, it can be brought to the lab and analyzed using a spectrometer. If you love any of the crime shows, mass spectrometry is one they talk about quite a bit. Often the identity of the compound, or at least really important characteristics, can be assigned in seconds or minutes. So it's really quick. Now, to interpret a spectrum, it's important to know how that spectrum is generated and understand what causes certain features in a spectrum to appear. And so that's what we're going to talk about as we go through these screencasts. We're going to start with a brief overview of what each spectra does, how it produces a spectrum. Then we're going to study how certain structural characteristics of a molecule lead to specific features in the spectrum. And then finally, we're going to learn how to interpret those features in a spectrum to derive aspects of the molecular structure. So we're going to go through all of these steps every time we talk about spectroscopy. So let's start with mass spectrometry. When we talk about mass spectrometry provides insight into the mass of a molecule and the fragments that compose it. And so when we're talking about the mass of a molecule here, we are talking about the molecular weight or the molar mass. That's one of the things that we see here. Now, this technique, right, will give us a mass spectrum. So when we look at and we talk about this technique, this is the part of the instrument that we're talking about, okay? This is a schematic of a mass spectrometer. What happens is a sample is injected here, okay? And to use a syringe, you inject it. That's called the sample source. and it's converted to vapor. So you heat to vaporize a sample. So we've converted it from a liquid to a gas, right? And so it's vaporized. Now, it's passed through a beam of highly energetic electrons, right? So we've got, this is an accelerating plate. It speeds it up. Here's our beam. You'll notice there's a positive and a negative section here on these accelerating plates. And so what happens here is the collisions with the electrons from this beam generate positively charged ions of the entire molecule and its fragments. So basically you're going to inject the molecule in here, the electron beam hits it, it causes it to be positively charged, right? And it also breaks the molecule apart into its fragments. That's how much energy is here. Now, these ions are accelerated through a magnet, and that magnet is going to separate them on the basis of their mass or charge, mass and charge. So as the ions impact the detector here, a signal's registered. And if you vary the magnetic field, it allows the spectrometer to measure the relative abundance of charged particles with a different mass to charge ratio. Now they have to be charged, okay? Now this is showing a generic mass spectrum. Each bar here is a mass peak that depicts the relative abundance of an ion with a particular mass to charge ratio. And that's what we're looking at here when we talk about this. Now we're going to go through each of these steps in the next couple slides. So the first step that we're going to talk about is vaporization. So you start with a small sample, and that's generally on the order of about 1 microliter. And you inject it into a spectrometer, very similar to how we inject samples into a gas chromatograph. And then it's immediately vaporized. So we have whatever matter we have here, mass of the compound here as a liquid. And then it's just going to go through a phase change and turn into a gas. Now, once vaporized, these gaseous molecules are going to drift along through a beam of these fast-moving electrons. Now, once it's vaporized, that gaseous molecule drifts through a beam of those fast-moving electrons and then undergoes electron impact ionization. Okay, so when an electron, now I'm going to abbreviate that as E minus, from that beam impacts a molecule, right, which that's the molecule in the gaseous state, an electron from that molecule in the gaseous state is knocked off. And so once we knock off an electron, electrons have that negative charge. Now we are going to produce a gaseous species that has one fewer electron and therefore a positive charge. So we produce a gaseous species with one fewer electron and a positive charge. And that's what we're going to detect in the detector later on. Now, this process of producing the molecular ion, okay, so we are going to produce this molecular ion. So an ion just means it's got a charge. And we are going to abbreviate the molecular ion as M plus with a dot right there. Okay, now that's showing 1 electron. And that's this process, that whole entire process is called electron impact ionization. Okay. Now, the positive charge, as we mentioned, appears because the negatively charged electron is lost, and the dot indicates that unpaired electrons left behind. Now, what we can further classify this as is a radical cation. Okay. Now, any species with an unpaired electron is called a radical. Okay, and so that just means that there's one unpaired electron that's called a radical. And so this is a radical cation, one unpaired electron and a positive charge. Now, electron impact ionization is very energetic, and it's enough to cause bonds in the molecular ion to break. When this happens, what we're going to see is that some of these ions, these bonds are going to break here, because that has so much energy, so the bonds are going to break, right? And some of these molecules will undergo a process called fragmentation, which basically means they break apart and produce lighter species, and these species are called fragments. Now, notice the fragments are charged and some are not. And we're going to discuss this later in greater detail in this chapter, but basically we can detect the ones that are charged, but we can't detect the ones that are uncharged. So that becomes important later. So two things happen here in the electron beam. The first is one electron leaves and we get this charged species that's a radical cation species that we can detect. And then bonds also break and we end up with fragments. So those are the two big things here that occur. Now, as we mentioned before, ions that are formed in the mass spectrometer, both that radical cation and fragment ions can be guided towards a spectrometer's detector through a curved tube by using a magnetic field, and that will bend the ion's path. Now, how much a given ion's path is bent depends on the strength of the magnetic field that's applied and the mass to charge ratio of that particle. Now, mass to charge ratio, we'll fill that in here. So the mass to charge ratio, and that's represented as an M over Z, where M is the mass and Z is the charge. Now, when the magnetic field is set to a particular strength, only ions of a really specific mass to charge ratio value can reach the detector. So basically we can zoom in and select these ions, okay? So ions that have a different mass to charge than that specific value will collide with the wall of the tube and will be totally destroyed before reaching the detector. Ions that are too light will be deflected too much, and those that are too big won't be deflected enough. So they won't make it around that curve. Okay, if you can kind of imagine it's like a racetrack and they just don't make it. Now, the detector is designed to keep track of the number of those charged species that collide with it, and that number is converted to what is called the relative abundance of the ion. Okay. Now, the greater the number of charged species that's detected, the greater the ion's relative abundance. So the more species that are there, the greater the relative abundance. So for example, there are more of these ions than these ions down here. Okay. Now, if multiple ions are produced with different M to Z ratios, then the magnetic field strength can be varied to determine the relative abundance of each mass to charge ratio. So we don't keep that number that kind of weeds out all the other mass to charge ratios constant, right? It's kind of like doing a scan so that we can detect all the mass to charge ratios. Now, what you see here is a mass spectrum. Okay, that's what it's presented as. It's presented as a bar graph with the mass to charge ratio on the x-axis, and that mass there, right here, is in atomic mass units. And if you remember way back from general chemistry, atomic mass units are represented with a U a lot of times. So just kind of be aware of that. And then the relative abundance on the y-axis, and each bar is called a mass peak. Okay, and so each bar is called a mass peak. Now, The process that's represented here in figure 15.1 is not the only one that can be used to generate a mass spectrum. There's a variety of other types of mass spectra that exist as well, each using their own particular method for generating a mass spectrum. All types of mass spectrometers, however, no matter what type it is, must produce gaseous ions from an uncharged sample, must separate those ions by their mass to charge values, and then detect the relative abundance of the ions having a particular mass to charge value. So each one of those instruments, you can take a whole class on mass spectrometry, but each one of those instruments has to produce gaseous ions, separate the ions based on their mass to charge value, and detect the relative abundance of ions based on that mass to charge value. It's worth noting that modern instruments use a quadrupole. Okay, now a quadrupole, quad means 4, so that's just 4 charged poles, right, to separate the ions. Okay, now this causes the ions to move in a spiral path rather than a bent path. And just more modern instruments use this. There are many different types of mass spectrometry, so it just kind of depends on which one you're using, but they all work under these same principles. Now, when a mass spectrometer uses electron impact to ionize a compound, the mass spectrum is more properly called an electron ionization mass spectrum. Okay, and so that's kind of the proper term for it. And then the charge on each ion that's produced by electron ionization is typically 1, right? And so in that case, that mass to charge is simply m, right? And so when we talk about this, there's a few abbreviations we need to be aware of. One is electron ionization, which is abbreviated as EI, mass spectrometry or mass spectrum. That's what we're looking at here. And then with this, right, the charge, which is Z, right, on each ion is just 1, okay? And it's plus 1. And so that means that mass to charge ratio, right, not ration, ratio, is really the mass over plus 1. And so that means it's just going to be the mass, okay? So when we look at this on this x-axis, everywhere there's a peak, we can interpret that as the mass of each fragment, which is very helpful for us, okay? We can figure out the molecular weight or the mass of every fragment. So when we're talking about the mass there, we're talking about the molecular weight. And so all the mass spectra that we're going to deal with in organic chemistry are this electron ionization mass spectra, and that's all that you're going to deal with in your packets as well. So we'll refer to them now just simply as mass spectra, but no, there's a lot of different types, but electron ionization is the one that we're going to want to be involved in. So let's look at hexane really quick. This is the mass spectra of hexane. When you're interpreting mass spectra, the very first thing to do is look at the highest peak. And by the highest peak, I mean the one that's farthest along on the x-axis. You're going to see that peak here is 86, okay? Now, this peak right here, that tallest peak right there, is going to be the molecular mass. So that's going to be the compound's molecular mass. And so if you want to take a second and calculate the molecular mass of hexane, which is shown right there, then what you'll see is that molecular mass is going to be right around 86 grams per mole. And that's what we see here in the mass spectrum. Now, a lot of times that's called the molecular ion peak. Now, the relative abundance, you're going to see the tallest peak, and that's the base peak. And that's just the one whose value is assigned at 100% there. So that means when these fragments went through the detector, there were more fragments with a molecular weight of 57 than anything else. Okay. Now, when we talk about this, what you're gonna see is that that base peak at 57, don't be surprised if you see that in the same mass spectra of other compounds. Okay, and we'll talk about why in a little bit. But big take home here is that this molecular ion peak here at 86 is the compound's molecular weight, or the molar mass. And so that's one of the things that we can derive from these particular mass spectrum. Now, there's a few other things that we can derive from that molecular ion peak. And so one of them is called the nitrogen rule. So if you have a compound and it contains an odd number of nitrogen atoms, it's typically going to have an odd molecular mass. And if you have a compound that contains an even number of nitrogen atoms or no nitrogen atoms at all, it typically has an even molecular mass, and that's called the nitrogen rule. So, for example, if you look at NH3, right, that molar mass is 17 grams per mole, right? Whereas ethane, for example, which is CH3CH3, is 30 grams per mole. Okay, so one nitrogen and you end up with a odd molecular weight, and then no nitrogen, you end up with an even molecular weight. And then, for example, if we looked at hydrazine, which is H2NNH2, that contains 2 nitrogen atoms, and so we end up with an even molecular weight, again, at 32 grams per mole. Now, this doesn't always work, but it works pretty frequently. Now, let's keep kind of looking at hexane. So I said in that original spectrum that we had, hey, look, we've got hexane, and we're going to zoom in, and we know the molar mass of hexane is 86 grams per mole. Okay. Now, we can also get in several other fragments, and that's where all the other peaks in the spectra came from. And these are fragmentation pathways, and they involve breaking the carbon-carbon bonds. So let's look. So these are all hexane here. And so they're showing in this image, it's showing the fragmentation pathway occurring here in red. And so what you can see here is that there's enough energy in that electron beam to break this piece off. And that becomes the uncharged species, and it's not detected. So the electron goes with, so one of the electrons goes with the CH3 here, and it's not charged. Now, this stays charged. And if you calculate up the molecular weight here, this CH3 plus CH2 plus CH2 plus CH2 plus CH2, that gives you a mass to charge ratio of 71. Now, if you look back at that mass spectrum of hexane, which I can't flip back to because it won't record properly. So go ahead and flip back and look at that. What you're going to see is in that mass to charge ratio, you're going to see a peak at 71. And it's this fragment peak where you've lost one CH3. So if you take 86 and subtract 71, right, you get 15, okay? The molecular weight of this is 15. So you can tell between that first molecular ion peak, and then the next one at 71, that you have lost one CH3 group. And you can see it's this fragmentation. Now, when you look here at the next fragmentation, so you're going to notice that big peak at 57, right? That was our base peak at 57. That's where you're seeing the fragmentation here, where you're getting a fragmentation of a CH2 group. So again, if you were to take 86 and subtract 57, and if you saw a jump there, it's because I had to find my trusty calculator, you would get 29 there, okay? Well, if you add up the molar mass of this, that molecular weight, right, the carbons are 12, so that's 24, plus 5 is 29, okay? So we could take 86 and subtract 57 and see that we've lost an ethane group. Then you're also going to notice a 43 there, okay? Well, on that previous spectra. Well, if you look here, you can see that we would break the hexane in the middle, okay? Now, when you do this, right, what you're going to see then is this propyl group. So if you were to take 86 and subtract 43, and again, let me get my trusty calculator, right? You would see that you would have 43. I should have been able to do that in my head, but I get nervous. So what you're going to see here is this molecular weight is also going to be 43. So you can use the spectra itself to see how the fragmentation peaks that you get. You're going to notice here that this is a symmetrical molecule, so don't forget symmetry. When we look at symmetry here, right, maybe you're going along and you're like, hey, what about this break here? Well, that break is the same as that break, just turn it around, right? So don't forget we get some symmetry here. Now, fragmentation pathways can be really, really complex. And notice you've got a lot more ion peaks that you get in the spectra than just those that I've presented here, right? We don't just have 86, 71, 57, and 43 in the spectra. The complexity of fragmentation arises in part because the pathways involve a very high energy radical species in the gas phase, and radicals themselves are just very, very reactive. Now we're going to talk a little bit more about some of these fragmentation patterns in a later screencast. But just I understand that this is not quite as each spectrum isn't going to be quite as simple as what's presented here, and we'll talk about that in a second. So let's do an example. All right. So using the mass spectrum of ethyl benzene provided, identify the molecular ion peak and the base peak. What is the formula of the ion responsible for the base peak? Now, if you go to the very next slide, which I'm not going to go to right this second, but you should have, you're going to see that there are some questions here, right? And the questions are these think questions that are going to help you solve this problem. And they include, what's the molecular mass of ethyl benzene? What corresponding mass peak could be assigned as the molecular ion peak? At what mass to charge ratio is the base peak? And how much lighter is the base peak than the molecular ion peak? And what bond could have been broken to produce the corresponding fragments? So when we think about this, there's a few things I want to point out here. First off, when we look at this formula here, right, the very first thing that you need to do in your mass spectra packet, particularly on your knowns, is that you're going to have a formula that looks like this, like some sort of molecular mass formula. And this molecular formula here is C8H10. Now you're going to have the names and you'll have to draw the structure, but then you're going to want to calculate the molecular mass. So the molecular mass there of this is 106 grams per mole, right? And so because it's 106 grams per mole, we can look right here and say, hey, look, that is our molecular ion peak, and it equals 106 grams per mole. Okay, that gives us so much information about the compound. In your unknowns, where you don't know the molecular structure, now you can look here and say, hey, look, that peak is probably going to be the one that's responsible for the molecular weight. And now you have the molecular weight of your unknown compound. Now, the base peak is going to be defined as the tallest peak, right, which is normalized at about 100%. So we're going to say, hey, look, this is our tallest peak. It is our base peak, which is right at a mass to charge equal to 91. And so that's what we're going to see there. Now, I am going to go on to this next area, right, because I've analyzed what I want on that particular slide. And so on the previous slide, we said, hey, look, the mass to charge here is 106 AMU, or grams to mole. And then the base peak there, the mass to charge is 91 AMU, or grams per mole. Now, the next question here is, what's the formula of the ion responsible for the base peak? And so here's where I want you to focus on the think. So to answer that particular question, we say, look, how much lighter is the base peak than the molecular ion peak? And so what we're interested in is, what is that fragment? And so what we can do then is we can say, look, I'm going to take 106 AMU and I am going to subtract 91 AMU. Now, this gives me a difference here of 15 AMU. And it says, what bond could have been broken corresponding to the fragment ion? Well, when I think about this structure, right, of this molecule, I have a CH2 here and a CH3 here. And so I'll look at this molecule and say, hey, I know that the first thing to break off is 15 AMU, or 15 grams per mole. That's probably this guy right here, which corresponds to 15 AMU. So that part has broken off. And so the fragmentation that we're probably seeing there is this fragmentation where that 15 AMU is related to the CH3.